Hey gang, welcome back for another video here on JoChem. Okay, so luckily kick back and relax because in this video I want to talk about something you all already know. This video is just going to kind of be one of those reminder videos as in, hey, I know we've been talking about all this new flashy chemistry, but don't forget that whatever we're discussing has this very, simple functionality that it's kind of easy to forget about. So similarly, when we were talking about enolates, right? We were doing aldol reactions, aldol condensations, Michael additions, Robinson annulations, and it was really easy to forget that at a base level, enolates were good nucleophiles that could just perform SN2. So in this video, I just want to talk about how 1,3-dicarbonyls, whether you have them in various flavors, whether they be just a generic, 1,3-true dicarbonyl with 2 ketones, or, something like this, which we would call a beta ketoester, because you can see that you have an ester, and since this is the alpha position, this is the beta position, that's why we would call it a beta ketoester. This, as well as, and I didn't give myself a lot of room for this, and it doesn't matter what type of, ester I'm actually drawing, or if you have a diester, these are all very similar from the perspective of how you can deprotonate them and use them for nucleophiles. Remember, in every scenario here, I'm only drawing one, but there's 2 hydrogens here that are highly acidic, because if we were to deprotonate in every scenario, let me just put base, 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 and I'm only going to draw this in one position, but if we had some base, something like, let's use potassium tert butoxide, T-butoxide, right? If we were to snatch up a proton and put a lone pair on that carbon that is sandwiched in between our carbonyls, we know this is a good acid-base reaction because in every scenario you can see that we have a whole heck of a lot of resonance available to us. And I definitely am belaboring this point a bit, but I just want you all to see that, we could swing electrons up here and kick them up. Or, in a different resonance move, we can do it here. We have this move available to us on each of these structures. So the point being is that, yes, we've been doing Claisen condensations, Diekmann condensations, but don't forget that whenever you have a flavor of a 1,3-dicarbonyl, whether it just be a regular 1,3-dicarbonyl, a beta ketoester, or a diester, you have the ability to deprotonate a carbon, or deprotonate, snatch up a proton, put a negative charge on a carbon, and just do some good old-fashioned SN2. So in this video, I'm just going to do a few examples, 3 or 4, and I just want to, do exactly that. Do some SN2, because sometimes it's very hard. We have a lot more things clouding our mind as far as, reactions that we're learning, mechanisms being shoved in. So sometimes, even if you kind of forget exactly what this would be called, like a reaction where you have a 1,3-dicarbonyl that you deprotonate to do SN2, sometimes you just have to rely on your foundational organic chemistry knowledge saying, I know that this position has acidic protons because of the fact that if you did deprotonate, you have a whole lot of resonance here, so the conjugate base you produce here is stable. Stable means weak, right? So that means this is a good acid-base reaction, and this proton is will readily fall off or be snatched up, whatever you want to call it. So gang, said a lot of words. Let me erase this, and we will head straight on to some examples. Okay gang, let's dive headfirst in to our first example. All right, so if we take a gander at what's going on, we see some arrows, some boxes, but again, never fret, right? Let's take it one step at a time. So we see our reactant given to us is what we would call, right, a beta ketoester, right? And at the risk of belaboring the point, right, remember it's because we see the ester and there's the alpha position and here is our beta position, right? So the name beta ketoester makes complete sense to us because the ester, alpha, beta, there's a ketone, bada bing, bada boom. Okay, so what do we got going on? In our very first step, right, we seem to have some ethoxide and some ethanol. So what that means to us, right, if we're gonna digest that, that means we're in a basic environment. Ethoxide's our base, and of course, if we're in a basic environment, that just means we have more ethoxide than ethanol. Okay, that's given to us, right, because we see the ether part of our ester is a 2-carbon piece, so it makes sense that that's the base we've been given. So all of this to us means, yes, we have a beta ketoester. We know that that carbon, alpha to both of our carbonyls right here, it's very acidic, right? That position is very acidic because if we deprotonate there, we get a charge at this position and it's resonance stabilized, right? That charge is delocalized. It's shared between a network of atoms. That means the acid-base reaction is super good. So if I'm gonna do my little work over here on step 1, all I'm gonna do is we would have a deprotonation step. That's it. Super simple. Step number 2, remember, here's the part, this is why I'm making the video. This part is just, we have a good nucleophile now, right? And we have a good electrophile. We have a good substrate, something that is primary, it has a good leaving group, super good for nucleophilic attack. So, all that would happen here is if we entered in our ethyl iodide, so all that serves to do is just alkylate that position that we deprotonated. Bam, right? There's the 2 carbons from up here. So in our very first mystery box up here, in a very, very pretty pink color, here is the answer we are looking for. Bam. And it's these 2 carbons right here that are new. That's the connection point. Awesome. Okay, so moving on, right? The reason why there is a second step, hopefully you're thinking of this, if you're sitting at your computer thinking ahead, it's because, right, you definitely see in the second step, we see the same, base that we were given in the first step, and then something else that is also very good for nucleophilic attack to occur on, right? It's the benzylic position, but it's primary, right, and it has a good leaving group in bromine. But the reason why that's possible is because this position right here absolutely still has another proton to be ripped off, right? This position can be made nucleophilic again by deprotonating it. So, over here, step number 1. It's just a deprotonation step, right? Sure, I'll draw in blue. But we'll have our ethoxide rip the proton off and dump the electrons onto that carbon that's alpha to both of our carbonyls, right? Didn't touch anything except the proton on that carbon. How do we draw this lone pair a little bit better? There we go. Then, step 2, enter in a good electrophile, something that is prime for nucleophilic attack. So, this is our answer in the box. Again, we reach for the pretty pink marker. I'm just going to go ahead and draw my beta ketoester part. I'm going to go ahead and stick my ethyl group way over here because I need to draw this somewhat bulky benzene ring. Oh, whoops, see, here I go, almost drawing it wrong. Be careful, don't lose carbons like I almost did. We have a connection point right here. That is the carbon that's in the benzylic position. Then off of that carbon, then we have our ring. So be careful, don't lose carbons. I almost drew the ring directly off of it, but remember, it's this position, which is this dotted carbon right here. Also, just in case you see some abbreviations along the way I drew this benzene ring and a carbon and a bromine, don't be surprised if you see something like this. If you see pH, pH just equals a benzene ring. So not the carbon outside of it, but just this part right there, okay? So this would be our final answer. So I hope you're seeing this is all I'm trying to get at. Don't forget that you don't have to kind of remember everything by name, right? Just if you have your foundations, right? This harkens back all the way to OChem 1. Acid-base trends, right? This is a resonance stabilized situation where you can see you can pinpoint where an acid-base reaction is going to happen. And if you just forget all else but remember that, that leads you through a problem. Okay, gang, let me erase this. Then example number 2. Okay, gang, let's rip this one simpler example, and then I have one more. I think it's kind of holistic, pretty cool, puts a lot of stuff we've done so far in OChem 2 together while still, you know, aiming at this topic as well. So, easy one, and then I think a fun one. Not gonna call it hard, because it's all fun. Okay, so what do we got here? So it looks like we have a diester here, right? But remember, it's still a flavor of a 1,3 dicarbonyl. We know we still just have this position in the middle. Shows a lot of nucleophilic character if protonated, because we know it is prone to be deprotonated because of the fact that a negative charge here is resonance stabilized. Okay, so if you wanted to give a little, this was more so just for terminology. Never get thrown off if someone's abbreviating stuff, just never panic, right? So we have this diester, and we see that the ether section over here is 3 carbons, right? So in this first step, where this is basically telling us we have a basic environment, don't be thrown off by the fact that the PR just means propyl. So this just means this, as well as, so we have propanol and a deprotonated version, right, with the sodium salt, so no big deal, okay? All this will aim to do, if we just do step 1, is a deprotonation. Didn't touch anything with the esters, just the carbon in between, okay? And then enter in our butyl chloride. So for step, be a little consistent with the colors. For step 2, all we're going to do is just enter in butyl chloride, and we have just some nucleophilic attack occur, right? More of a pain to redraw the whole thing than actually reason through the problem. 1, 2, 3, 4. Our answer is the diester with a newly alkylated position with 1, 2, 3, 4 carbons. There's our original piece. There's the 4 carbons. Easy peasy, lemon squeezy. Okay, gang, I hope you're seeing this is not like a mind-blowing video. Just taking some concepts we've been working with and then just remembering, hey, we can do Sn2 here as well. However, I think if you can jive with this last example, then you're starting to kind of see the bigger picture. You're starting to see how things can be connected, and you're truly starting to see the things you're learning in OChem 2, some of the stuff you learned in OChem 1, and stitching them all together. Okay, let me erase this, and we'll cook up the last example. Okay, gang, last example, let's get it. All right, so we see we have a multi-step complete the reaction problem. Never ever fret, just look and take it one step at a time, quite literally. Okay, so we start off with this 3-carbon aldehyde propanol, and let's look at our very first step. The very first step is LDA, negative 78 degrees Celsius, and THF. Luckily, so these conditions right here, just strong, basic conditions, right? Throwback to our beginning enolate days, right? We knew this would be conditions for kinetic enolate formation, right? Well, lucky for us, in this scenario, we are just going to form an enolate, and we don't have to worry about the thermodynamic enolate versus the kinetic enolate, because in this position right here, this aldehyde, we only have 1 alpha carbon to deprotonate, right? This is the only carbon right here that we can deprotonate. So for step number 1, and I'm going to draw like these arrows out over here. For step number 1, And don't freak out, I'm gonna draw the structure of LDA. Okay? I believe that's correct. Right, what's gonna happen is we are just going to deprotonate the alpha carbon and form an enolate. So I'm just gonna expose one hydrogen, show it getting picked off, one proton, and the formation of our lovely, lovely, lovely enolate right here. Okay, this is it. The result of step number 1. Okay, so I'm gonna kind of draw a dotted line. I'm gonna use the space going this way. So for step number 2, okay, so for step number 2, PCC. Oh, okay, so here's the trick. I almost forgot myself. The trick here is that you form an enolate. Wanted to make it tricky. We have an enolate. What are we doing with it? Why is PCC the next step? The idea is here we're going to do a homo-aldol reaction, okay? So in this step right here, basically, this is all kind of in step 1, if you will. We're going to form our enolate, and then that enolate is going to bump into another one of itself, but in its carbonyl state. And then we're going to do an aldol reaction. So, electrons swing down. Remember, these electrons in the double bond, because remember, this is just nothing but this resonance form, right? We know that the alpha carbon's nucleophilic. We attack, electrons kick up. So I'm gonna go ahead and just keep this going. We have this reformed over here. I have my dot carbon right here. I'm gonna go ahead and asterisk this carbon right there. I know my dot is bonded to my asterisk. The asterisk has an O- on it. And then I have 2 more carbons, bam, bam. Okay, cool. Everyone's connected to everybody. So maybe this right here would be more explicit if, like for example, let's say I made this 5, I made this 4, I made this 3, and then I put like a 2, I put like a line, and then second step of just water, just to, you know, for this part right here, this would be the workup. We would just grab an H off of water. So after the aldol reaction rather, we would have this right here. So this is just an intermediate. The result of steps 1 and 2, okay? So what do we do with step 3? We see PCC. Remember, our OChem 1 days, this is going to oxidize our carbonyls. So step 3, and this is like 1 and 2. We're just going to oxidize, so this aldehyde won't change. It's already oxidized as much as it can be by PCC. This alcohol becomes a ketone. Bam. Okay? So, number 4. What are we doing here? Well. Wouldn't you looky here. 1, 2, 3. We have a 1,3 dicarbonyl, and in this instance, it's not a diester, it's not a ketoester, it's just a dicarbonyl with 2 ketones. Okay? So, what do we have here but a carbon, alpha to both of them, with a proton that is absolutely begging to be ripped off, right? So, between steps 3 and 4, I'm going to save some space. All we have is potassium tert butoxide as well as T-butanol, just a mixture. And all that's going to happen here, and I'm not drawing the potassium spectator ion, we don't really care. All that's happening is just a deprotonation reaction, right? That's a really, hope you can see that arrow. Just grabbing this and dumping the electrons onto this carbon. So the result of that looks like this. And I'm drawing the electrons on the other side just for space purposes, okay? And bringing it back to the theme of the video, we see entering in at number 5, ethyl bromide, a perfect electrophile for an SN2 reaction, something perfect to attack, because we have a primary carbon with a good leaving group. Excellent substrate. So, for number 5, we just enter in ethyl bromide. Whoa, hold on, let me make sure I do this attack without leaving group leaves. So I'm going to draw the result up here. And on this carbon, we have a new 2 carbons right there. Okay, gang, so what I like about this example is that it brings together a lot of the old, some of the new, and some of the even newer, okay? I know this wasn't a situation where you had to decide kinetic or thermodynamic enolate, but based on those reagents, I guarantee you were thinking about it, right? These were kinetic enolate conditions. We knew it was just some simple alpha deprotonation because we only had 1 alpha carbon. Then there was a homoaldol reaction, right? We had to think. We weren't given a second carbonyl to attack, but we did see some workup. Sorry about the presentation of the problem at first, but it was just the enolate attacking its original self as a carbonyl, and then the workup with the water right there, then some oxidation, some throwback, some great memories from OChem 1, and that only bumped our secondary alcohol up to a ketone. Then some deprotonation, right? Some of the new, right? Just taking the carbonyl or the carbon alpha to both carbonyls in this 1,3 dicarbonyl, deprotonating it, making it nucleophilic. Then rounding things off with just giving a good substrate primed to be attacked via SN2, alkylating that carbon alpha to both of the carbonyls, bringing it home. Whew. Gang, thank you for staying with me through the first, through the second, and through the third examples. Don't forget, whether it's a regular enolate, whether it's smushed in between 2 carbonyls, whether they be ketones, aldehydes, esters, don't forget SN2. It can happen. Okay, thanks for joining this video. Thanks for watching. I appreciate you, and I'll see you in the next one.